Okay, so the theorem that I'm going to prove for you now is that if T is a tree with n greater than 1 vertices, then it has a leaf or a vertex of degree 1. Okay, so here's the proof. And this proof is a little different than the one presented in the book, but I love it so much. So you'll see two different points of view. You can see this video and the one in the book. Okay, so the way this one starts is we say, since there are finitely many edges in T, the length of a path is bounded. Since there are only finitely many edges in T, the length of any path in T is bounded, because remember, in paths, I can't reuse edges. So the length of a path in T is at most the number of edges in T. All right, so because the length of a paths can't grow arbitrarily long, there must be a longest one in T. In fact, there could be several that are the same length, that are all the same length longest path. It doesn't have to be unique, but I'll say so. There must be a longest path in T. And now I'm going to list the vertices of one of the longest paths. Okay, so suppose we list the vertices of one of the longest paths in order. And so these vertices are maybe V1, V2 through VK. All right. And so I'm going to show that the degree of the first and last vertices of a longest path in my tree have to both have to have degree 1. Okay. And that's essentially the short story is that if those are the end points of the longest path, if they had degree greater than 1, I could either make the path longer or I'd have to get some kind of a cycle. So that's what we're aiming to show. Okay, so we'll show that the degree of V1 and the degree of VK, so that there's the two endpoints, are both equal to 1. And we're going to proceed by contradiction. So we proceed by contradiction. So let's suppose the argument for V1 is the same as the argument for VK. So let's just do the argument for VK, all right? So let's suppose that the degree of VK is not equal to 1, so that it has to be bigger than or equal to 2. Then, well, what does that mean? It means that VK is connected by an edge to the vertex that came before it in the path, VK minus 1, and at least one other vertex that I'll call W. Okay, so I'm going to draw my little path to give you a visual here. So here's my path, V1, V2, dot, dot, dot. Who knows what comes next? Here's VK minus 1, and here's VK. And so really there are two cases. there are two cases. One case is that the vertex W is on the path. So what does that look like? Let me draw it for you, okay? So I start at V1, I go to V2, dot, dot, dot. Somewhere on this path is the vertex W. And then dot, 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 I have VK minus 1 and VK. All right. Well, since I'm assuming that the degree, I know that the degree of VK is at least 2, and it's attached to 2 vertices. VK minus 1 is one of them, and W is another. Okay, so there are 2 edges, at least 2 edges coming out of VK. And what I can see here is that I get a circuit that goes on the path from W to VK minus 1 to VK, and then takes that edge back to W. In fact, it's a cycle. So we get a circuit. In fact, it has to be a cycle from W to the circuit that has to be a cycle, and I'll say maybe it goes follow the path from W to VK minus 1, then to VK, and then back to W. So that's a contradiction because our tree is not supposed to have any circuits. So contradiction because T has no circuits because it's a tree, right? Okay, then what's the other case? Well, the 2 cases are really W is on the path or it's not. So the other case is that, maybe I'll put a 1 here for the first case. The second case is that W is not on this path whose vertices I've enumerated. Well, then what goes on then? I claim we have a contradiction right away, because if W isn't on the path and there's an edge from VK to W, I could have made my path longer. So this is a contradiction because then we could add W to the path and make the path longer. But we chose this path because it was one of the longest paths, okay? So like there is a longest path length, and this was one of the longest paths. Therefore, we have to conclude that every tree has a leaf, as we had claimed. All right, thanks a lot. I will get back to you with other videos proving those other 2 theorems, okay?